This is Smarter Cars, a podcast about autonomous vehicles.
This is the finish line. The Stanford racing team has made its way into the history books.
But the most important thing for me is it actually doesn't matter who comes first. It matters that we as a community achieve it.
Early in a technology, a thousand flowers should bloom.
Welcome to Smarter Cars. This is your host, Michelle Kairouz. Our guest today is Philip Koopman, a professor of electrical and computer engineering at Carnegie Mellon University. He's spent more than 20 years researching embedded systems and automotive safety, including safety for autonomous vehicles, and that's the subject of our conversation today. Phil, welcome to the show.
Oh, it's great to be here.
Great. So you are a professor at Carnegie Mellon. Can you tell us a little bit about your academic background and the areas of research you've been working on and tying it into how it relates to autonomous vehicles?
Sure. I actually started out in industry for a few years, so I have a lot of dirt under my fingernails, and I switched over to the professor track mid-career after spending quite a bit of time doing embedded system hardware and software. And when I came to Carnegie Mellon, I started doing software robustness, software reliability. And right after I got to Carnegie Mellon, it turned out that there was a project called NavLab where they did a no hands across America. Back in the late 90s, they went DC to San Diego, 98% hands off the wheel. Wow. And I joined that team as the safety guy.
Great.
And since then, self-driving cars have run hot and cold. And I have been an embedded system person who does a lot of dependability. I've done a lot of safety work in just traditional cars even. And more recently, as self-driving cars have become hot again, I've gotten back into it in a bigger way. Right now, a lot of my research is stress testing autonomous vehicles. So I may say AVs or autonomous vehicles, but self-driving cars, sure, basically the same deal. But I say AVs because sometimes they're not cars you'd see on a street. They're like automated army tanks and things like that, or big convoy trucks. And so we spend a lot of time. Yeah. Well, they're out there running around in tests right now, and they build them, we break them. That's basically the deal.
Great. So one of your areas of research is with respect to safety for autonomous vehicles. And I'd love to dive into some of that with you today. Just to give the lay of the land, I think we can all agree that today there is no formal standard for safety for autonomous vehicles in terms of government safety standards. So there are lots of open questions out there as companies are developing autonomous vehicles as to what the level of safety should be, how we should measure it or demonstrate it or test it. Let's maybe start at the beginning. What level of safety do you think we should want for autonomous vehicles? If you were in charge, what would the level of safety be?
I think the best way to attack that is to sort of go after one of the premises I hear that people have in their head when they ask that kind of question. And I know you've dug around in this space a lot, the details, but let me just sort of lay out what's going on here. Because when people say, oh, there's no standard for autonomous vehicle safety, that's not entirely true. And it's important to tease that apart, or else you'll end up with people saying, well, there's no standard, we do whatever you want. That's not true. For baseline cars, even though the U.S. government does not require it, there's been a set of international standards for 20 years. There was one in the 90s for just ordinary car electronics called MISRA. There's a newer one that came out, half a decade ago at this point called ISO 26262. It's a lot of twos, a lot of sixes. But if I say the ISO standard, that's what I mean, because it's a lot of twos and a lot of sixes. But that's a functional safety standard that applies to most parts of a car. So if an autonomous car person says, oh, standards don't apply, we're not doing anything. Well, come on. The brakes still have to work. The engine's still not supposed to take off on you. And ISO 26262 deals with all that stuff. So you should be at least following that, I would hope. There's a more recent draft standard that's sort of in process called SOTIF, Safety of the Intended Function. And that's supposed to deal with things where even if the software is perfect, maybe it only works sometimes because it's a radar and once in a while you get a return, once in a while you don't. And that's coming quickly to being a standard, and that's something people will be able to figure out. But the hard part in terms of, well, what do the standards not cover? The standards right now don't cover the machine learning part. And that's the hard part. So if you want to ask, what do I think? I think you should be following ISO 26262. You should be tracking and following the SOTA standard, which is pretty straightforward stuff. Other industries like aircraft already know how to make things that feel operational safely. And the hard part is the machine learning, and that's the part I guess we should be talking most about, because that should be the part that's a little tougher to get your arms around. Although I certainly have ideas about it.
Yeah. So sometimes when people talk about the machine learning piece and the control of the vehicle, they talk about, well, the standard should be that it's safer than human driving, or,
whatever that means.
Yeah.
That's actually a really hard question right there.
Yeah. Let's dive into a little bit about that. Obviously, we're not comparing an autonomous vehicle against one perfect human driver with perfect vision who isn't drunk, isn't drowsy, isn't distracted. When people compare to human driving, what are they really doing?
I think a lot of people doing that should think a little more deeply about what they mean when they say it. Because let's say, well, on average, there's so many fatalities per so many million miles, and you see numbers like 100 million. New York taxi drivers are more like 130 million. Although that's the medallion drivers, the other drivers aren't as good. So I'm going to, without saying that this should be the right number, let's just use 100 million miles for fatality as a number, as a starting point, right? It's a number like that. It's not exactly the number. Well, fine. Okay, let's say you can get an autonomous vehicle to have the same fatality rate. Then you could claim you're just as good. But wait a minute, that number includes all the drunk drivers, right? And includes all the 16-year-olds. And includes everyone else. So it's an aggregate number, but and you have to decide if that's really good enough. Do you want to factor out the drunk drivers? Do you want to factor out all the inexperienced drivers, and then you get a number that's higher? Maybe it's 130, maybe it's 150 million. At some point, society sort of has to agree what the number is. But let's say you come to a number. You're not done yet, because what if the autonomous vehicles are good at some things and bad at others, and the things they're bad at are what a human is good at? What if the people who die in autonomous vehicles have a distinct demographic characteristic that's different than the general population? That's going to get messy in a hurry.
Right.
Do you remember what happened with airbags when they first came out?
Yeah, they killed small people.
They killed small people, and women are smaller than men.
Yeah. And
so
children.
Killed women and children, and that was bad. Now, the people who did it, as far as I know, they didn't see that one coming, and I think the issue was they were using male crash test dummies. But it would be no surprise whatsoever if a similar kind of thing happens with AVs, because that's just the way it is. If you haven't figured out, where the weak points are, there's going to be a weak point, and it's going to be a surprise to you. So even if it's the same, it won't be the same because different people are going to die. And so you want it, people like me say, well, I want it to be way better, not the same. I want it a lot better. And that's in part it. The other part is, how do you really know you got the number right?
Yeah.
Maybe say it's 100 million, but it's really half that. How would you know?
Right. What, it's interesting that you mentioned, should we take out drunk drivers from the measure? When I think about an accident caused by drunk driving or by distracted driving, isn't that really like all of the other accidents that are caused by human drivers, in the sense that it's either a failure of perception or a mistake in measurement or a failure of control? It may be that you didn't see the tree because you were drunk or because you were looking down at your phone to send a text, but it's all part and parcel of having that mistake or failure on behalf of the human, and whether that's because you didn't apply the brakes hard enough in a rainstorm or you were texting. These are all mistakes that humans make. It seems like that all needs to be included if we're going to do it on a statistical basis, because isn't that part of the criticism of human driving, is that they are subject to these mistakes or flaws?
Sure, that's one way to go. You can argue it. I haven't reached the point where I really know what the answer to any of this is, but it's important to get the debate going and have it be an informed debate. One of the things you can say is, well, if bad human choices account for basically all accidents, then shouldn't you subtract those off before you judge the car? And it's going to have to be 10 times better. On the other hand, if you say, well, fine, there'll be a net savings in human lives, fewer people will die, that sort of by definition means that things other than distracted driving and drunk driving are going to kill people in autonomous vehicles. And people might have a problem. You're going to end up in a courtroom where someone's saying, well, a human driver would not have made that mistake. And in the general population, it's a little easier to talk about, well, half as many people died. It's a lot harder when it's someone in your family that wouldn't have died. And the people who are alive because of AVs, it's hard for them to know that that's why they're alive, right?
And that's
the ones who didn't get in a crash. How do you identify them? So this is a very big social thing. I mean, I'm an engineer by training. I don't know that engineers are the right people to figure this part out, but we can inform people that these are what the issues are.
Right. And, I think what you're getting at is, if a human makes a mistake in perception and, I just didn't see that car coming when I pulled out, you're saying we're sort of more likely as a society to be willing to forgive that than a computer-driven car where the sensor just didn't pick it up.
Well, I think that the way the system works, it's going to be harder to argue that the machine is okay, because it's like, well, the machine should have seen it. How come it didn't see it? Mm-hmm. That's going to be hard. The other one is machines are going to miss things that are different than what people miss. And the argument's going to be a person would have seen that issue, they would have, done the right thing. And never mind, the computer's better than people in some spots. It'll probably be worse than people in other spots. And when a mishap happens, you're going to focus on the thing that went wrong that a human wouldn't have gotten wrong. So this is going to be really tough. I mean, it's sort of, it's sort of this societal good statistical argument. If the AVs are 1,000 times better than people, there'll be some mishaps. They'll be unfortunate, but it'll be pretty easy call for most people, right? It's 1,000 times better. But if they're only a few percent better, that's a lot of mishaps that are going to be due to things that people are having trouble understanding why I couldn't have gotten that right.
It's kind of interesting when you look at the statistics also, because, the only statistics you really have to use are, these accidents that get reported to the police or accidents with fatalities. Is that really the full measure of, dangerous human driving?
Well, it's obviously not, because there's a lot of very serious injuries, a lot of minor injuries, a lot of property damage, and focusing on the fatalities. I mean, ultimately, that's an issue. But another thing to consider is that the AVs might have a different profile. I don't know how it's going to turn out, but what if it turned out that they never have a fender bender and they never have minor accidents? They don't have any major accidents, but they kill twice as many people. I don't know if that would be, and you'd probably say that's a weird thing to think, but I'm worried about correlated failures. So if you have that different profile, it's hard to evaluate that. And by correlated failures, what I mean is, what if an AV doesn't know the concept of a bridge washing out and they just keep driving off the broken bridge, right? You could have a whole mess of problems in one spot. What if the AVs go crazy on daylight savings time, which sounds weird, but every daylight savings time, look at the news for how many computers crashed, right? You don't know. And the correlated events are what bother me. Yeah. Yes, they do. Their driving ability degrades from lack of sleep, but it's not because the clock did something funny. It's a little different.
Right. So are humans good drivers?
Well, ask anyone, and almost anyone will tell you they're above average.
Yeah.
That's the Lake Wobegon school of driver.
Right. That's the problem with the relative nature of it. If you say, well, gee, I want autonomous vehicles to be better than human drivers, everyone's going to say, well, I'm a great driver, so it's not going to be a better driver than me. But that's the problem with the relative comparison, I think.
Well, when it's tough, do you really want to trust your life to someone who's not as good a driver as you are, because it's only average, right? That's
Right.
tough.
Yeah.
Right? Although some of it, I think, again, if you have an AV that is way, way, way better than human, hands down better than human, this becomes easy. But if you start arguing, well, we should introduce these things when they're basically the same, that's when it gets kind of fuzzy. And to go back to something I said earlier, this is actually the big thing. There was a study from RAND that said, well, even if AVs are only 10% better, there's a net savings in life. And all that math makes sense as far as it goes. The issue is, how do you know it's actually better? And we're nowhere near being able to know it's better. People say cars don't make stupid mistakes, don't make bad choices, therefore they'll be better. So what about the part where we don't know if they're good drivers or not, right? Yeah, they don't make mistakes, like drinking and driving, but we don't have enough data to actually know they're as good as even a normal human being. We just don't have that data.
Right. So let's talk about that. Let's talk about how we can measure or demonstrate safety. I mean, I think you've mentioned a few general safety standards out there, but there is no government standard for this question of how safe does the artificial intelligence that's driving your car have to be. So right now, if cars are put on the road, I think companies would be self-certifying in their own view as to what is safe. But what are some? Let's talk about some of the ways that you could demonstrate that autonomous vehicles had reached a certain level of safety. I guess some people have suggested that we could just, administer a driving test like we do for 16-year-olds when they get a driver's license. Can you explain your view on that approach?
Sure. That has a lot of intuitive appeal, but there's a big problem with it. So people say, sure, just give it the same driving test you give a 16-year-old, setting aside whether you're happy with a fleet of 16-year-olds driving around your city. Let's just set that one aside, okay? And say, okay, 18-year-old, whatever. There are actually two parts to a driving test. And the first part is, those of us who had a driver's license got in a car and we drove around. I know when I had my driver's test, somebody ran a red light right in front of me the first minute. That was fun. But I recovered. I got my license. You show your skills. They made me do the parallel parking and the U-turn and all that other stuff. Great. Okay. But that wasn't why I got my driver's license. It turned out I've been driving off-road since I was about 14 because I grew up on a farm. I've been driving for years. Why didn't I get a license? Well, because you have to be 16. They just don't trust you to have the maturity and judgment till you're some age. And we can argue about 16 or 17 or 18, but it's not 12. It's not 8. And so the other part of the driving test is, okay, fine. You passed the driving test. Where's the part that shows me you're as mature as a 16-year-old to not do stupid things like drive in a snowstorm where you're not equipped, you don't have the skills to drive in. Where's that part of the test? That's not part of a standard driving test. So if you really want to go down that route, you have to have some notion of maturity and being able to demonstrate not only can the AV do all the skills, but does it have mature judgment? And that's hard to test that way.
Right. So you're saying that, without some sort of technological maturity, you're missing a piece in testing. And is it also just part of the problem being that for a 16-year-old that they can do a certain number of skills, and you're basically inferring that they can do the rest of the skills of driving once they've demonstrated a few, and we just don't know how to extrapolate that with.
Well, that's only part of it. Part of it is, are you going to do stupid stuff, right? Yeah. Part of it is also, we're taking for granted that they've had 16 years of learning how to recognize what a person looks like. And so the driving test doesn't really test, do you know how how to tell if a person's in a crosswalk. It's more about vehicle maneuvers and things like that. Why? Because the 16-year-olds had 16 years to figure out, yeah, that's a person, that's an animal, that's something. Here's how I avoid hitting something. And so really it's a test about ability to display all those 16 years worth of learning in the context of moving a car. But where's the part where, how do you know that the AV is actually going to recognize all different sizes, shapes, colors of people with hats on and Halloween costumes and who knows what?
Right. So if we can't administer a test to figure out if an AV is safe, what are some of the other ways we can demonstrate safety? I know there's the idea of testing on public roads. There's using some sort of proving ground or obstacle course and computer simulation. What are some of the other concerns about these options?
Well, there's a couple pieces. And the short version of the first piece is that when you're riding in an airplane, they didn't prove it was safe just by flying it around. The FAA actually had people making sure it was engineered well. And now we're back to ISO 26262 and the other standards about make sure the engineering is there to begin with, right? So it's not just horrible code. Okay, but moving on to the machine learning part, which is the part that we don't really know how to do that with yet. Sure, you do some road testing, you do some simulation, but even if you do that, you have a couple problems. The first one is you have to make sure this simulation is actually realistic compared to the real world. But the really hard one is, how do you know what to simulate? If there's an object you've never seen and it's not in your simulator and you run into it in the real world, I almost said hit it. Hopefully you don't hit it, right? But that's the point. Here's an object you've never seen. What's going to happen? And people say, oh, we drove around and saw a lot. So I'll give you one of my personal stories of something that happened to me when I was a fairly young driver. I'm driving on a highway in a convertible. At max speed limit, it was 60 or 65 or whatever it was back then. This is before 55 happened. And okay, fine. I'm driving at this speed and a giant blue tarp blows off a truck full of gravel, completely covers my car at highway speed in a convertible. So it's actually on my head and face, right? And this is a truck-sized tarp, complete blackout, can't see anything, going at speed. I saw it out of the corner of my eye, and I said, okay. Oh, and by the way, it's an overpass, so that means there's a bridge abutment I can hit if I'm not careful, right?
Oh, gosh.
and figured out how to basically do a blind stop to save the vehicle and get the tarp off me. And I tell this story once in a while when I'm doing talks, and people are like, okay, add that to the list. But the problem is there's an infinite number of things on the list, and you're not going to see them driving around even for a million miles. That's one you may not ever see, right? But when it happens, you need to be able to deal with it. Now the counter argument is, well, that happens less than once every 100 billion miles. I don't know what the number is. It's got to happen more often than that happened to me. But you could say, there's a few really rare things we're just going to take our lumps because on average we're safer. Okay, but I don't really think anyone has a handle, or at least publicly talking about how often these weird things are. And it isn't that this one's very rare. It's that there's so many of them. In aggregate, they're sort of steadily arriving, and it's hard to predict the next one that's going to happen because they're all different from each other. Now, there's ways to deal with this, but that's the thing that I worry about with safety is, sure, you fix everything you see, but the stream never stops.
Right. What about, extrapolating to the more general use case? In other words, do you have to know specifically how to deal with a tarp flying off the back of a truck, or can you just have experience that when something happens that blocks your sensors, regardless of what it is, that, you're going to go into a mode where you reach some sort of, you attempt to reach some sort of safe state?
Well, that's a great way to think about it, because if you try and do every particular weird thing, you're never going to get there. And so you have to this is back to, do you have a good engineering process? So if I want someone to have a safe AV, I would trying to evaluate it, ask questions like, okay, so this tarp flies off the truck. What's the lesson you learned? And if the lesson is look for tarps in midair, that's the wrong lesson. The lesson is, hey, wait a minute, you just got complete sensor blackout. What's your plan for that, right? And then it doesn't matter how you got blackout, if it was paintballs or or mud being sprayed in winter that covers everything. Who knows? So that's part of it, is to generalize. The other part is that if you wait for it to happen to a vehicle, someone's been put in a situation the vehicle can't deal with. So you need two pieces. The first piece is the vehicle needs to know when it doesn't know. It needs to know something's wrong that it doesn't know how to deal with. Because that's the strength of people. It's like, I don't know what's going on. All I know is I better do something. As opposed to a vehicle that says, oh, yeah, everything's fine. I don't see anything, right? So that's part of it. The other part is you're going to have to do some testing. That's sort of out-of-the-box testing that tries to just throw weird, unpredictable stuff that might or might not be perfect, realistic, but sort of stresses the system past its limits to make sure that if it goes past what it knows how to do, it does something reasonable. Now, the worst thing is, for example, and there was, what I read in the news was this actually happened in one of the crashes, is an AV gets in a crash and doesn't realize it's in a crash, and it tries to keep driving, right? It doesn't know that it didn't know how to detect a crash. That kind of stuff is kind of scary.
How does computer simulation fit into the picture with, you mentioned sort of testing edge cases, and maybe that could be done on an obstacle course. Maybe that's done
simulation. You really want to do that in simulation, because the obstacle courses, you just can't do enough tests that way.
You can't think of enough different scenarios to test in real life. If you train an AV on simulation, does that work transfer over cleanly to real life driving? How do you feel about that process? How good is the simulation?
Well, it all depends, right? There's a famous saying that all models are wrong, but some are useful. Okay. And there's a lot of truth to this, that every simulation, is a lie in some sense. But sometimes it's useful because there's questions you're asking the simulation. And if the simulation gives you a very high quality answer to that question, it doesn't matter if the rest of it doesn't work. You're only interested in one thing. And so probably what you really need is more than one simulation. And for the folks, the areas that have been doing simulations for a long time know this lesson, that you don't want to find a software bug in your anti-lock braking system by running vehicle level simulations. That makes no sense at all. It's a really expensive way to find something you could have found a lot easier just by simulating the one component. And so what you're going to find is that every simulation has simplifications. When I said lies and they're wrong and stuff, what I really mean, it's simplified. And there's a simplification. And so if you have a simulation that's trying to test geometry and avoidance of geometric objects, and you populate it with smooth cylinders, that's great. Now, when you get to the test track, you have to worry about things that aren't smooth, things that are lumpy, things that aren't cylinders, things that move around. And fine, the worst thing to do is go to the test track and do 1 million tests on a test track with smooth cylinders. Once you do a few, you know that the simulation results are going to still work in the real world. You should be concentrating not on what you simulated, but on the parts of the simulation that were oversimplified. So you actually end up with a bunch of levels of simulation, and each simulation takes the level below, make sure it still makes sense, but concentrates on, all right, that simulation simplified the following thing. That's what I'm going to beat on. And if you think about it this way, closed course testing is actually a simulation. You're not simulating the car, you're simulating the environment, the stuff that the software simulation can do. Road testing is a little different. It isn't really a simulation. In fact, you shouldn't be testing safety on the road. That's a strong statement. What you should be doing is you should be collecting requirements on the road. And you should have high assurance you're safe before you ever get on the road. Now, we should go back and talk about the big red button. But, ideally, you should actually have a really good idea you're safe when we go on the road. And you should be using the road to say, look at that giant blue tarp. Didn't think of that one. That's okay. And the car should be doing something reasonable when it encounters something that, that isn't, that it goes, I have no idea what this is. All right, I'll do something reasonable. Now, I know that's different than what a lot of people say they're doing. They say we're testing on the road, on public roads. And the issue with that is it puts other people than the people in the car at risk, right?
Well, assuming that there's some level of safety, people have a reasonable comfort with what the car is doing before they start on-road testing. It seems like some amount of on-road testing in complex environments is helpful for seeing if you're right and moving forward and seeing what the next level of steps are. But it does give you some level of comfort. I mean, at some point you have to test in a real environment before you deploy, right?
Well, yeah, but let's dig into that because I think this is important. The first thing is you can do data collection without testing in a real environment. That doesn't put anybody at risk, correct? You're just collecting data. It's not autonomous. Now, that only gets you so far, and I recognize that. The second thing is if you actually are testing on a road, you need an argument to make sure that people are safe. And the typical argument is there's a safety driver, and they have the big red button or some other disengagement mechanism. I'll call it a big red button. I know that sometimes it looks for pressure on the steering wheel or pressure on one of the pedals and all, but it amounts to a big red button. I'm going to take over because this thing's doing the wrong thing. And that's good, but the problem is the big red button isn't necessarily built right or doesn't always work or might paint the driver into a corner. And so when they're doing public testing on public roads, there's an issue of safety of everyone else on the road as to whether or not the big red button really works. And it's not a given. Not everyone gets that right.
But that's true. I mean, if that argument were carried out, I mean, that would be true of all cars that ever get tested, right? Not even just autonomous ones. You're really, you're right. At some point, something could fail, right? You're saying, the safety driver doesn't take over. I mean, I think that's always a possibility, but at some point, once you have a level of comfort testing on a closed course or in simulation, people have to have some level of comfort before they put cars out there. But it seems like on-road testing is reasonable if you have some level of safety that you've achieved, before you get there.
Well, that intuitively kind of makes sense, but there are a couple issues there. And I'm just going to talk about what the issues are. I'm not going to necessarily say how they should be solved. One of them is that for a car to deploy, it has to conform to the Federal Motor Vehicle Safety Standards, FMVSS. And that does things like says, when you press the brake pedal, sure enough, the brakes are really going to work, right? There's no FMVSS for the big red button. So it's at the discretion of the team whether they think it works. So that's a new thing. There's no regulation for that. The other kind of issue is that there's a tremendous amount of pressure on these companies to deploy, right? And one thing I've learned in the safety world is anytime there's a lot of pressure and there's no external oversight, that's a recipe for some teams just feeling so pressured they may be acting in good faith. They may convince themselves everything's safe, but if somebody who weren't under the pressure took a look, they'd say, no, guys, you really can't do that. So there's a risk of that happening.
Yeah, I guess the counter argument there is that, the counterbalancing that risk is also the risk of liability and the risk of poisoning the public perception of the product and all of those things. So, I think there's this pressures, on both sides of some of these issues.
Sure, there are pressure both ways, but some companies are going to decide to roll the dice, right?
So, okay, well, I think I understand where you're coming out on-road testing and
yep.
and computer simulation.
Actually, let me follow up. There's a way to solve that. That's not an impossible problem. All you have to do is make sure your disengagement mechanism conforms to ISO 26262, which is an accepted safety standard, and you're done. That's really all it takes. There's no machine learning in there at all. But right now, there's no requirement to do that.
Okay. One of the challenges that people talk about in demonstrating safety in AVs is the fact that it's hard to know why the car did what it did, whether it's a repeatable thing, whether it was the car got lucky, whether a slight variation would have a different outcome. And people talk about this as AI being a black box and the interpretability question. Do you have any thoughts on that issue and how the challenges of using deep learning or other types of programming can be managed in measuring safety?
Sure. The reason we started by saying machine learning is tough is because machine learning learns what it learns, and it's very, very difficult, in most cases, in practice, impossible to know what it learned. And machine learning is sort of good at gaming the system and learning things you didn't think of. So I'll give a made-up example to give the example of the type of thing that could happen. Let's say you're training on a test track and everyone has an orange badge on. Maybe it's a transponder or an access pass or something. For all you know, the car learned not to hit things wearing an orange badge. And the first time it goes on a road, no one has an orange badge. It's open season.
Right.
Now, for sure, a responsible developer would never let that happen. And you made the point you need to do on-road testing. Well, that's one of the things you're going to find out pretty quickly on on-road testing. And hopefully the big red button's working because you're going to need it, right? But that's an overly simplistic example that it learns all sorts of weird things. And it has blind spots that you never saw coming. The unknown unknowns are tough. So it's hard to validate because it doesn't think like humans. It doesn't really think at all. It's just a big association about pattern recognition, basically. And so that makes it tough. And so when you're trying to validate these things, you just go, well, what is it doing? And so let me switch gears, come in another way, and then I'll sort of join up the threads. Let's say you have a test with a kid in crosswalk, and the car doesn't hit the kid in the crosswalk, and you repeat the test 10,000 times, and 10,000 times the kid, preferably a dummy, right, doesn't get hit. Okay, great. And you conclude that the cars won't hit kids in crosswalk. Okay, well, alternative one. Let's say you only do the test once. How much assurance do you have that it saw the kid? Maybe it just swerved because it saw a gun wrapper. Maybe it saw a shadow. Maybe they use random planners. Maybe it just got lucky. So you run it 10,000 times, you claim statistical significance, but that's not the same as causality. You don't actually know if it saw the kid. You're just saying, what are the chances it got lucky 10,000 times in a row? Well, part one, that's expensive to run those tests. Part two, what you really want to know is, did it see the kid? Not, did you get lucky? So a lot of this validation will be simplified by having the machine learning sort of give a little introspective narrative of what's going on. Hey, I see a kid. I'm going to steer around the kid. Well, if I run that test 10 times, I have a lot more confidence that, it saw a kid, especially if when there's no kid, it doesn't say, I saw a kid, right? You run a bunch of tests like that and you say, all right, it's still statistical analysis, it's still correlation, but I have a much warmer and fuzzier feeling that stuff is working the way it's supposed to if I design a test and it can correctly tell me what test it's in.
Right.
Now, that's not necessarily how machine learning usually works. The guys who do end-to-end machine learning, it's just a giant black box and it does what it does. But if you want to validate safety, what I'm suggesting is maybe you want to design your machine learning a little differently to say, all right, one of the things we need to learn is how to explain what we're doing. That makes it harder, for sure. But what you're trading off is ease of design versus ease of validation. And at some point, validation is going to be the hard spot. So it's important to spend some resources on that.
Okay. So you have identified, some concerns with driving tests, concerns with on-road testing and simulation. What is your view of a methodology that you could get comfortable with to show safety for autonomous vehicles?
Well, I'm not going to claim to have the silver bullet, but
you're not.
No, I'm not, as it turns out.
What could you get comfortable with if you were in charge of a company putting one of these cars on the road and you needed to sign off that it was safe to do that? What would you want to see in terms of processes in order to get comfortable as to a level of safety?
Well, I want to know that, first of all, I'm following all the standards that are already out there. There's no reason to make up your own stuff. People know how to get this stuff right. And that's going to take care of a lot of it, not all of it, but it'll take care of a lot of it. Once you're following all the accepted industry standards, industry themselves writes these standards. So they're pretty suitable. Once you're done with that, I mean, the big thing that's left hanging over your head is the whole machine learning business. And that's tough because machine learning requires a lot of training data, a lot of testing data. You're going to want to do a lot of on-road testing. And I'm going to say it's really data collection. People call it testing, but it's really about the data collection. It's about, oh, look, there's something we haven't seen before. That's key, as much of that as you can. But you're never going to get it all. It's not going to happen. You can't afford to. And so you want to do a lot of simulation, but for the simulation, assuming you do the later approach to do the speed versus realism trade-off and get all that straight, the thing that's left for you to deal with is how do you know that you put all the objects in the simulation you need to? How do you know you ran all the weird scenarios? How do you know you did all these things? For example, we've done some research where we just introduced a little bit of haze. Just a light haze. And all of a sudden, people just drop off and it stops seeing people. You look at it and say, wow, there's a person there. And the computer's, nope, no person there. A little bit of haze. Nope, no person there. So you have to basically do, I guess, what we're calling perception fuzzing, where fuzzing is a term that you take some data and you scramble the data a little to see if the system falls apart at the seams or not. And so you need perception fuzzing in a couple different ways. You need it for the operational design domain. ODD is the terminology. And that ODD is something like, well, we only run in downtown Pittsburgh and we only run on sunny days. And we only run when the sun's not coming in at a low angle coming into the front. And we only run when it's not rush hour or whatever. There's some description of where you run, but it's more than just where you are. It's the environment. It's whether or not the camera lenses have been cleaned recently. There's all these restrictions, and you have to have a precise description of that, and you have to be sure that if any of those assumptions are false, they're false. So you're not running in an area that's unsafe and you didn't even realize it. So that's part. You have to make sure you really understand the operational design domain and enforce it. And the second part is there's all these objects and events. So you need to fuzz those as well. You need to, for example, in simulation, you start pasting people in the middle of the street. You start pasting people in that are mangled a little bit. There's one with a weird hat on. There's one who's really skinnier than a normal person would be. And you try and find where the limits are that this thing breaks, just to make sure there's no weirdness that you didn't see coming. So if you do a lot of fuzzing in simulation, that gives you more confidence. Then we get on the road, weird stuff you didn't think of isn't going to nail you. So if we did all that, I'd feel, pretty good. What I'd really want, though, is I want a written safety argument. So written safety argument is we're safe because we covered these 10 bases or 20 bases, whatever it is. And for each base, we know that base is covered because we did some combination of simulation and testing and design reviews. I'd really want a written document that says, here's why we're safe, something I could defend and say, no, we thought of everything. And this part, sure, you can never guess what weird thing's going to happen. But our analysis and testing shows that 99 times out of 100, even if this thing you never even thought of happened, sure enough, we're still safe. Maybe 999 times out of 1,000. I don't know what the number is. But I'd want to see that argument because then I've applied engineering rigor instead of just driving around saying, looks okay to me, right? Mm-hmm. Now, I know the car companies aren't just saying, looks okay to me, but nobody has publicly revealed that they're doing the level of rigor I'm talking about. And if you're a safety person, that's what you want to see.
So when you say level of rigor, that's a combination of kind of on-road data collection and testing and computer simulation. And is there something else to this kind of rigorous design engineering process that you have in mind?
Sure. You want to know the software actually works, right? That your machine learning execution algorithm is actually high quality software. And that your training data isn't biased somehow, that your training data hasn't been corrupted. So it's just about, for every aspect of your design and testing and validation process, are you winging it or are you following a defensible engineering plan? And so it's just as much about the process of doing the engineering as it is about the actual code that's running or the actual data that you used. And the rest of the world outside of autonomous vehicles, that's how everyone else does safety. You can't just say, oh, we're different, we're not going to do it. It's true the challenges are significant, But that doesn't mean you can abandon engineering rigor. You need to do something defensible.
All right. Final question. Do you think that NHTSA or others in the federal government should specify a standard for safety? And if so, would that be a federal motor vehicle safety standard or some other rule?
Well, it's interesting because the government is looking at FMVSS. Some of the players say, oh, FMVSS doesn't apply because we don't have a steering wheel. I'm simplifying, but that's the general idea. And I think that those can be changed in a way that will be effective by saying, well, yeah, the test requires turning a steering wheel, but what it's really after is ability to turn or ability to stop the car, whatever, right? Yeah. There's no brake pedal. Well, don't need to do a braking test. I'm sorry. Yes, you do. but yes, there's no brake pedal. What was it really doing? It was doing stopping distance. Fine. Show me your stopping distance. So in terms of the existing FMVSSs, I think that just going back to why the test is there is a way to deal with it. But the FMVSSs all assume there's a responsible human driver in charge, right? And they need to be augmented, they need to be changed. One way, my favorite way is I understand there's this tension that if you demand 100% rigorous safety and federal regulation, people say it'll just take too long and people unfortunately die while we're waiting. I completely understand that argument. There's a way out of that. There's a way out of the box. The way out of the box is say, fine, look, you're an AV vendor. You have a choice. You can conform to FMVSS if you want, but if you don't want, that's fine. Please explain to us in writing why you think you're just as safe. If they want to run faster than the government can, put the burden on them to say, fine, show us an argument. Explain to us why your stopping distance is okay. Great. And that gets rid of having the government create a test that doesn't work because somebody chose a different technology. If they want to basically not conform to standards, in principle, I'm okay with that. But the safety argument, the thing I was talking about, still has to be there. We just have to have a different one. So I'd be a fan of a transparent safety argument. And transparent doesn't mean public. I know there's proprietary interests, but there's outsiders who can come in and take a look and see if it makes sense. And so that's sort of my solution to this is make a transparent safety argument, explain to us why you're safe. And if you want to get a waiver for regulation, explain to us why your alternate is safe enough. And have somebody who doesn't have stock options on hitting the release date say it makes sense.
Right. So there is no, you could comply with all the FMVSS today, right? You could have a regular car with a regular steering wheel, but you've added self-driving technology and it might drive itself into the wall, right? You could comply with the current standard, so it wouldn't require an exemption, but should there be something else on top for more of a performance standard for driving ability?
I think there should be, but the government hasn't enforced that for normal cars, so they're not inclined at this point to enforce it for AVs. There's the whole issue that the FMVSS does not deal with software quality. It's basically, for the most part, still assumes everything's kind of mechanical. All right, we applied the brakes once, it worked, good to go. We took our foot off the accelerator pedal, car slowed down, good to go. And that sort of doesn't deal with the reality that software does weird things only once in a while. And so there's a whole sort of blind spot in the federal regulation dealing with software safety, and it affects regular vehicles or ADAS, the intermediate technology, just as much as autonomous vehicles. Now, again, the safety standards I mentioned sort of do deal with that stuff, but they're not required in the U.S.
Well, this is going to be an interesting discussion going forward as we see what the government does and what companies do. Thanks so much for taking the time to talk with us today, and it was great to hear your perspective on all these issues.
Well, Michelle, thanks for having me. I really appreciate the chance to be on your podcast.
All right. Thanks so much. Bye-bye. Thanks again to Phil for joining us, and thanks to all of you for listening. If you enjoy the podcast, please subscribe on iTunes or wherever you listen to your podcasts. You can find the show notes for this episode on our medium.com publication called Smarter Cars. We look forward to seeing you next time.